All right, guys, take a minute, look at these bellwork questions, and do your best on them. All right, there's the answers. I haven't really checked these, so if any of them are a little wrong, that's okay. I just really want to focus on this last one. So explain why you think Frank's swimming rates are proportional or not. Probably not, just because it's unlikely that Frank would be swimming constantly at the same rate. So whatever his swimming rate is, I guess 50 yards per minute or whatever it is. It's probably unlikely that he maintained that exact speed over the duration of the race. It's an Olympic distance triathlon, right? So, it's usually by the end of a race, experiencing some fatigue. So whereas speed may have started a little bit fast, it's probably not as fast at the end of the race. So that's why it would be probably not proportional. All right, read it again. I can find unit rates from tables, graphs, equations, and stories. Bam! Take a minute and copy this down. A computer programmer determines how much to charge based on the lines of code written. Is this situation proportional? Let's find out. Okay, now tables like this one is built horizontally, not vertically, which is usually what we're used to seeing. But it won't matter. In fact, it won't even matter in this case that the Y's are on the bottom and the X's are on top. We'll talk more about that here in a second. But remember, in order for this to be proportional, all the values as fractions have to be equal, right? So I'd say, 50 divided by 1,000, is that equal to 100 divided by 2,000? Well, to check that, I'm just going to put in the calculator, 50 divided by 100 should be 1/20th right there. That would be a simplified fraction on this one, okay? Now, this next fraction, right, you could say, well, I'm just going to cross out the zeros, which also shows 1/20th. So these two are equal as of right now. But we need all of the fractions to be equal in order for this situation to be proportional. So I would continue on and see if this is also equal. So 150 over 3,000. And yes, that is also 1/20. You can check in your calculator, that's good. So far, this situation is proportional, but we also need the last one. And this is usually where I don't, but whoever does the worksheets is like, hey, look at this last one. It wasn't proportional after all. Gotcha! So just be careful. Make sure you check all of the relationships and make sure they are proportional. Well, 200 divided by 4,000 still gives me 1/20th. So this one, it just happens to be equal. So is this proportional? Yes. In the past, students only check those first two, and they're like, see, the first two are equal, therefore it's proportional, and then the last one's jacked up. So make sure you check all of them in order to make sure it is proportional. Based on the table, how much does this programmer charge per line of code? Yeah, well, let's look, right? Well, these fractions that we just figured out actually will tell us the numerator, all of these top values. So on this one, right, we got the numerator, which is lines of code. And then the denominator here is all shown in cost, right? So that'd be like one line of code for 20 bucks. And it shows that way for all of these values, which means that we can figure out pretty quickly in a proportional relationship a unit rate like this one. Because it's asking how much they charge per line, or you could say one line. And right here, yeah, just like you guys said, it's $20 per line, okay? Per one line. And you could have written that with a slash instead. But either way. So $20 per line of code. I'm just going to put per line, one line, because I already wrote enough there. Use this unit rate this unit rate is also called the constant of proportionality. That's true, because it is the rate of change for a proportional situation. So we only say it's the constant of proportionality for proportional relationships. I just call it the rate of change. We're going to call it something else in a later unit, but just understand it is going to come back. But for now, constant of proportionality is fine. Rate of change, I think, is a little bit better, because it is a rate, a comparison of dollars and lines in this case. All right, we go. Number 2, John is participating in a walk-a-thon, and each sponsor pledges $5 plus 150 per mile walked. Figure out the rate of change and determine if it's proportional. 1 minute, go! I like problems like this one because they gave us at least the first answer, the rate of change on this one. Now, it's not always a unit rate, but this one just happens to be the unit rate. It's telling us how fast, or I guess how much money each sponsor is giving, which in this case is $1.50 per mile. Now, again, if you put 1 mile on that, that's fine. Okay, but that is the rate of change. And we do want these simplified. So if you said like $3 per 2 miles, just know that it's not fully simplified, okay? We want, well, I guess that means it is a unit rate. So proportional or not, this one is yes or no, but the answer is not yes. It's no. This one is not proportional, even though the rate of change is consistent, because they are pledging $5 in the beginning, means that we don't have an initial starting value of 0, which is required for proportionality. So like if you were to graph this, just real quick, not that I'm going to actually graph it, but you got X and the Y-axis like this. This line, it would have a constant rate of change, so it is straight like this. It starts right here at $5. Okay, but we remember, hopefully, that in order for this to be proportional, it would have to be a straight line that goes through the origin, that orange dot right there. Now just think about it like this, you guys, is that whoever the sponsors are, they're saying, you know what, we'll give you $5, and if you get injured between now and the start of the walk-a-thon, you take that $5 for the charity. But if you do walk as far as you can, because we're going to give you $1.50 per mile. All right, a booster club was washing cars for a fundraiser, and they recorded the amount of money they had received and the number of cars washed every time they had a break. How much did they charge to wash each car? Find the rate of change and see if it's proportional based on that table right there. 1 minute, go! So we want to know how much they charge to wash each car. Well, in order to do that, we're going to have to go into the table on this one and figure out some values. And we'll see how consistent it is throughout. It should be a constant rate of change, though. It'd be kind of weird if they were like, you get charged $10 and then you get charged $8. I don't know. So on this one, we want to figure out how much it changed from row to row on this one, because this is a vertical table like this one. So we can see it went up 7 car washes. And then the amount of money went up, let's see, I did $60. No, it wasn't $60 right there. It was $52.50. I just put that in the calculator. And some of you guys may be wondering, well, how did you get $52.50? I did $165 minus $112.50. All right, so that shows a change in dollars of $52.50 for the 7 car washes, right? Now, I can figure out the rate from there, but I just want to figure out the other ones as well. Okay, so from $165 to $225, that's a $60 change right there. Now, notice as well, instead of it being 7 car washes, this time it's 8 car washes. And then finally this one, so $277, I got to put this in, there we go. $277.50 minus $225. This shows another change of $52.50. Now, even though it may be equal to the 7 car washes, which it is right here in green, that does not necessarily mean that it will be proportional, okay? And again, right now, all I'm doing is figuring out how much they charge per car wash. So now I'm going to make these rates, the comparison of change in dollars to change in car washes. So the red one shows it was $52.50 for 7 car washes. I'm just going to put CW right there. And it shows that would be $7.50, that's a 0, for 1 car wash. All right, now that should be our unit rate, but let me just check with the other ones. So the purple one, right, it was $60 for 8 car washes. And when I divide these, I also get $7.50 per car wash. Now, if for some reason this was inconsistent, it wouldn't have a constant rate of change, which does happen from time to time. And then, of course, that last one, the green, is the red one right there. So we can go back to the question now, which was how much do they charge for each car wash? Yeah, it was $7.50 for each car wash. Okay. Well, then the question becomes, what is the rate of change? That's all we need. It was $7.50 per car wash. Now again, that is a unit rate. It's not always, the rate of change is not always a unit rate, but it would make sense to compare this in a per 1 car wash scenario. So the final question is this proportional? It's a great question. Worksheet. So on this one, now we need to go back to the table, right? I'm going to look at this first row, and it compares $112.50 for 15 car washes. Now I'm going to simplify this in the calculator. 112.50, I typed that in wrong, over 15, and that would show $7.50 per one, right? Which is, it does match the rate of change, which is important in order for this to be proportional. Now, again, I'm going to check all these other ones though. Okay, so I'm going to check the next one. Well, what about 165 over 22? Yep, 750 over 1. Okay, so these are equivalent fractions, right? I need all of them to be equivalent though. So what about 225 over 30? Bam, 750 per 1. And then the final fraction, 277.50 all over 37. And sure enough, the calculator gives me 750 per 1 on this, okay? So is it proportional? The answer is not no. It's yes. This one. Bill gave you a graph showing how far he was from home. You got to figure out how fast he was traveling, the rate of change, and then determine if it's proportional. 1 minute, go! So we want to know how fast Bill is traveling, I guess, on this one. Let's take a close look at the graph here. Now, something about this graph is we don't want like values that are going to give us decimal values in these. Here's what I mean by that is like this point right here, it's not really useful for us because we're going to have to do some estimating on points like these ones. Okay. What I mean is that the time could be a decimal value and then the distance could be a decimal value. Not necessarily just a decimal value either, but also an estimated decimal value. We want exact values that we can use in order to figure out the rate that Bill is traveling at. So on this one, what that means for graphs when we start figuring out rates of change like we're doing here is we want the line to go through these grid corners. Okay, so like the origin right here, that's a grid corner. Okay, so I'm looking at the boxes. I need to go through any one of the corners of the boxes, and those red dots do not go through the corners as close as some of them may be. But if I look at this next one right here, yep, that's going through the corner of a box. So I can use that point, but I'm not going to use the red ones. I'm going to get rid of those garbage. Well, from here, the graph is going to tell us the speed at which Bill was traveling. And I like to make a little stair step like this, you guys. You don't have to, but I like it. Well, this is going to show me the change, right? So the distance first for me. And it shows the distance this way. That's the up and downwardsness of Bill's line. It shows he went from 0 all the way up to 60, right? So that was 60, and it's showing in miles because it shows miles right here. Well, how long did it take him to go those 60 miles? Well, now I'm looking at this green line. It's coming up. There it is. And how many hours did that take? Well, it started at 0 hours here, and then he went to 2 hours right here. So that took 2 hours. Well, this will help us to figure out the speed at which Bill was traveling, and I'm going to show it as 60 miles in the 2 hours. This is 60 over 2. And again, it is a rate, so I do want the labels on these so that I can specify it. And yes, this can now be simplified. Going back to the question, how fast was Bill traveling? Well, 60 miles in 2 hours. It is the same as 30 miles in 1 hour. Well, then we may ask ourselves, what is the rate of change? It also is still 30 miles per hour. Yeah, is this one proportional? It's a graph, and it's a straight graph. It's a straight line, that blue one, and it does go through the origin, so this one is proportional. Julie created a graph showing how much money she had in her savings account and how much was she saving each month, and then we'll figure out the rate of change, and also if this one's proportional. Actually, I'm going to answer that last question first. Is this proportional? Well, that is a straight line. It's just not going through the origin, so automatically no, it's not proportional. Bam. That's pretty quick. So let's figure out how much he was saving each month with this graph. All right, so I got to look at this graph. I'm looking at the blue line right there, and this is going to help me to figure out how much money she was saving each month. So right here it shows at 0 months, that's 0 months, she was saving $15, or she had $15, which also is what makes it not proportional. And then also for 1 month, bam, $25. That would be this point right here. And then, we could see these other ones. 2 months, $35. 3 months, $45. 4 months, $55. 5 months, $65. And 6 months, $75. But I prefer just to focus on those first two ones, the red and the purple one there, the left. So, in fact, I'll zoom in on this. We know it's money and then months, okay? So we got to figure out how much it changed. Well, the change in this amount, it shows, right, it's kind of going upwards. It wouldn't matter if it's going down, by the way, yet. Because I'm just looking for a change. Well, it went from $15 to $25. That's a change of $10 right there. Well, how long did that take? Well, I think that was 1 month. I'll zoom out just to check. Yeah, it was 1 month. All right. Well, what is this as what does this tell us? How much she was saving per month? Yeah, it tells us she was saving $10 per month. Okay, so we'll go back, and then that's the answer for that first one. How much was she saving per month, each month? There it is. Well, we just figured it out. It was $10 per month. So what's the rate of change? $10 per month. Okay, so I hope you guys are making that connection. The rate of change is, well, it's kind of the unit rate, I guess. It's the unit rate of change. That'd be fine. I guess we could say they're the same. That's fine. Which of these situations has a higher rate of change? Explain how you know. So a lot of students look at these two lines and it's like, hey, it's the same line. Well, it's not. It's not the same line. And the reason it's not the same line is because of the scales. Okay, and that's the numbering. The scale is the numbering for your x-axis and y-axis. They are different. Okay, so for example, over here, let's see. I don't know. I guess this one's a little bit more clear. This relationship that shows 1 and then I guess 2 to 1. It's a 2 to 1 ratio. By the way, both these are proportional. So all the ratios are going to be 2 to 1 on this. All right, 2 to 1. But this other one, right, if I went, I guess that looks like it's about 2, but that's more than 2.5. So, well, I guess a 2 to 1 ratio would have been like right here, right there, or I guess even like right here, right? So a 2 to 1 ratio shows a steeper line, which means that the B graph shows a higher rate of change. It's the B1. And again, how do we know that? Well, the B graph is showing a 2 to 1 ratio. The A graph, which I did in purple, is showing a less than 2 to 1 ratio. Yeah. And again, I'll go back through that because I heard someone ask a question there. A 2 to 1 ratio would be like 10 to 5 or 5 to 2.5, about right there. Or even, I guess 15 to 7.5, something like that. We can see that that blue line is lower than those 3 purple dots. And yeah, it's 0, 0. It's still proportional. But I kind of missed right there. Let's try it again. That's okay. That's about as straight as I can get that thing. So it's a lower steepness, which means that it has a lower rate of change. So is the rate of change always the same as the unit rate? Well, as long as you're looking at changes, then yes, that's fine. Now, if you said, well, how much does it cost for 1? Well, if you included the initial value, then you could say no. So it all depends on how you're defining this stuff, and there's probably not as much uniformity in this as I'd like, so I'm going to leave that one blank. It's yes or no depending on what you explain. So like this one, right? Like what I had. No, if it were, then it would be a proportion, but not all situations are proportional, which is true depending on how you define it. Now, number 8, how do you find the rate of change from a table? You just take the change in the dependent variable and divide it by the change in the independent variable, just like we did with that one table. It kind of looks a little bit like this, right? You'll see the boxes like this, something like this, and then you'll say, this is the change here, and that's the change there. This is the dependent variable, that's the independent variable. If they did it backwards, then they are jacked up. How do you find the rate of change from a graph? You just find the change in the y values and divide it by the change in the x values. Now this is consistent because in a later unit this will represent rate of change, but we call it something else. So always think about it as dependent over independent, or y over x's. And yes, I understand you guys may have learned about dependent and independent variables in science. That's because they stole it from math. The jerks! I can find unit rates from tables, graphs, equations, and stories.